Alright, time for another DraftPhysics.com, debatephysics.com, or DraftScience here on YouTube. Eek. Anyway, video presentation, discussing physics, the elemental universe, how it functions, how everything that does something, happenings, events, yes, events in reality, how does it work? And the simple argument is that the science community collectively, has jumped to a bunch of conclusions, and they're all going to tell us it has to be that way and can't be any other way, and they're going to assert to us that they have done all this hard work and figured out all the answers, and they're frankly silly answers, frankly. And you shouldn't be fooled that they really haven't done any of the hard science, in the sense that they haven't tested this stuff to prove it. They've just gone where they're flights of fancy kind of thing. They want a woo-verse, and they've created one, and so they're just as guilty as the religious kooks, and they're accepting a theory merely because it creates some sort of pleasant fluctuations in their neural network. Somehow it gives them a little happy feeling or something to think the universe is all wooey and fun, and on purpose, really. I mean, if you're going to start believing in ESP particles, this is, it's so ridiculous. It's so ridiculous. Anyway, so this subject is light, okay? Giant subject, and he spends 3 minutes and 55 seconds on it. Yeah, so just sort of like, the title of the video is "What is Light? Maxwell and Electromagnetic Spectrum." 3 minutes and 55 seconds. Why bother? So it says, up till a couple of centuries ago, so we had no idea what light is. So there's lots of theories. And frankly, there were people who understood it could be little bits of stuff flying through space. And they were right. And the silly nonsense theories they accepted in the end are wrong. There's no medium, there's no ether, nothing's waving, okay? There's plenty of stuff, okay? But it's stuff flying, little bits flying. Quanta, as Einstein put it. Okay, energy quanta. It seems like magic, no? Question mark. So, but then he says there is no magic in this world, really. So again, but yeah, your theories are completely magical. There's nothing, they're not tied to anything called reality, and they don't make any sense. And your own observations prove them ridiculous. So they have this idea that a single electron produces a single photon. Can't be done that way, and they already know it because they know when they try to polarize light or do something else to screw around with it, it has a giant polarization, okay, thousands of atoms, and it can't possibly hit one electron if it's that big an object, so to speak. Just stuff we don't understand. So let's understand light a little better right now. So through James Clerk Maxwell and the electromagnetic spectrum. So let's understand, Maxwell was an etherist, okay? And so, yeah, he had a bias, and he biased his description as a wave theory. But there's nothing in the math that requires you to see or believe in a wave of any kind. It's just about frequency. And frequency is important if you understand tipping things over. So they always use some kind of well that they're trying to knock something out of, when the real key to it is understanding that you can add energy to a system if something is swinging in the right direction. The direction you're adding energy, you add energy to the system. If you try to add energy to a pendulum while the pendulum is opposing you, it won't work. Okay, you'll take energy out of that system. So clearly, the tipping point argument is the sensible way of understanding that you have to have the resonant frequency of any kind of oscillating that the system is doing, and you have to add your energy. If you're going to add energy, you have to add it, okay, constructively to its previous condition. And, it provides a very good explanation. So clearly electrons think we'll just draw some of this stuff. I think that's what we'll do. All right, so I mean, they often draw. First they don't even. Oh, that's a little too contrasty. All right, annoying software glitches. Anyway, okay, so I don't know. It's all this stuff matters, but it's the fact that they have this description of an atom as if it has a bunch of orbiting electrons, and the argument would be is now the electrons aren't orbiting. They're just in a position, and in that position they're under constant tension, so they're constantly jittering in their position. Okay, so they're constantly doing some of this, and the truth is that when you can make them jump much further, okay, from say a position here to a position here, okay, which would be higher energy the more condensed it is. So you could sort of understand that if this was a positive here in the center and you have these negatives, that the ones close are in very strong tension and the ones further away are kind of weakly held. So that would be another simple, a fairly easy, safe deduction, is that the ones on the outside are loosely connected to the nucleus and the ones on the inside are tightly connected to the nucleus. So anyway, anytime the electron moves from one position to the other position, it's essentially doing this into the environment. And if it does this fast enough, it means that all the stuff that was going to hit the hand here ends up hitting the hand here. Okay, so I've condensed it in space, in the sense I've contracted the space that it'll be in. So you could understand that something happening at a frequency, if there was three bullets coming, and I move this forward, I'm going to blue shift them. Okay, I'm going to convert them into a smaller, a tighter frequency. And so the simple sort of argument is that photons are created by electrons, but it takes more than one to make a photon. Okay, so the photon itself is an event. Okay, it's more than one thing happening. It's a series of events, and they happen at a frequency, and the key is the frequency either adds energy or subtracts energy from the surface it's hitting. I have to find the eraser. So the idea is there's a bunch of energy in the universe all the time flying in. Okay, so we know there's a ton of this infrared radiation that goes into surfaces constantly. It's getting bombarded by radio waves, microwaves, all kinds of heat. Okay, thermal energy. How better to put it? Well, anyway, so it's bits with kind of a wide frequency. And obviously the surface can accelerate that frequency or decelerate it, in the sense of making it longer or shorter depending on the activity of the electrons. So if the electrons are doing that jumping from being close to the nucleus to being on the outside of the nucleus, that jump would be a push out, okay, out into the world, and it would be increasing the frequency of anything that was coming in. So infrared radiation would essentially be turned into visible light. And so a surface isn't emitting a photon. It isn't creating energy and spitting it. It isn't shooting something it has and it's losing it. It's not losing matter, okay, or substance or even force when photons are being released. All it's doing is pushing out into the universe. The electrons push out, and when the electrons push out, they create a higher frequency bit of reflection. So the thing reflects at a higher frequency that will be visible. So you're just converting infrared radiation into red, green, or blue visible radiation. And then you can convert red, green, and blue visible radiation into ultraviolet radiation, and then you can change the ultraviolet into X-rays. So you can, by just jumping, by just doing this process of compressing what comes in, okay, blue shifting it, and then red shifting going the opposite way. So you're expanding the frequency of the energy when you're receding, and you're compressing, condensing the frequency making a higher frequency when you're pushing into the field. So every surface is vibrating, in that sense. And if the vibrations are significant enough, that is, if you are actually jumping electrons from one energy level to another energy level, then you're going to succeed in causing this effect of compressing the energy coming in. All right, so that's one way of explaining it. Then antennas are a whole nother subject, but I mean, it's a way of understanding that the speed of light is dictating what makes it all very regular. So the idea would be as if you sent electricity, a pulse, into an antenna. The idea is that the antenna is going to cause atoms, okay, to do that ionizing thing. And as they do that pushing of the electrons, they're going to send the signal. And you can understand that at the speed of light is the electricity has to travel. So obviously the first bit, will travel quite a distance. And the next time it happens, it'll be less distance. The next time less. So you're going to end up with a polarization built into creating the frequency. So you create a compression here, then you create another compression, and that ends up being a photon. So the photon requires there to be more than one event, and that's sort of made obvious by the fact that it has polarization. The photon isn't just a frequency, it's a thickness, a polarization. So it's the little bits are all going the same velocity, the speed of light, in one direction, and they're just separated from each other in space in the other dimension. Yeah, that's a simple enough brief explanation. Let's see what else I have to add. All right, another huge giveaway that this is about radiation that's just reflecting off of a surface, that these colors are just a reflection of the environment, and that's all they are, okay? And they're, so what comes in, something can come out, but nothing radiates the actual photons. Nothing generates them. And all you can do is something hot, again, is going to do this thing. See, my shirt by itself isn't saying, oh, I have to do a bunch of electrons flying off at different energy levels. It's not ionizing radiation. And once you get to something ionizing, then you can start producing visible light. You can start increasing the energy of the photons that are hitting the surface. So I'm not emitting a bunch of ultraviolet light or some other kind of light. I'm not doing a lot of increasing of the energy because I'm not burning hot. All right, so but you can tell from magnets. Magnets are the real giveaway, because you can understand that a regular bar magnet, a piece of I can make a piece of iron into a magnet by just stroking it with a magnet, and it'll become magnetized. And you know that it's not excreting magnetism. It's not creating some kind of thing inside of it that's creating something shooting out of it. That all it's doing is changing how the energy coming into it is being, through equilibrium, expelled. So energy goes in, energy comes out. The simple truth is that you can change the character, the pattern of the energy, and that's all we do, is we just change the pattern of the energy. So it hits me in one form, some of it's reflected tomorrow, some of it's reflected immediately. The stuff reflected immediately will show you a color, the stuff reflected tomorrow won't. All right. The stuff not reflected is the stuff being absorbed. That means the energy is reducing the frequency rather than getting increased. So that's the photons in phase are in resonance with the vibration. That color will be absorbed, and the colors not will be reflected. Something like that. And it's really just about the fact that nothing makes the photon. The photon is it's just taking what's already in the field and changing the pattern that it is in. All right, so yeah, that's probably, it'll have to do.
Since we've been able to look up at the sun, we've been aware of light.
So the question I could ask is what temperature does the surface have to be at for it to look like a sun? So I mean, how much hotter would you have to make the Earth to make it glow like the sun, to burn on the surface? And a few thousand more degrees, and yes, the Earth would be glowing hot. Okay, so, and that's really all you're saying, is that there's enough vibrating where it's increasing. Okay, the energy going into the sun is coming, goes in infrared and it's coming out visible, because there's enough of this going on, this moving of the electrons.
As darkness is one of very few things that we instinctually fear.
I don't even know if that's true. We fear darkness. I don't know. So says you.
We have always bestowed light with God-like.
I mean, every night I go to sleep, but I'm not all that afraid of it. It's kind of comforting, to close it all off and, disappear.
Properties. But for all of antiquity, we had no idea what light.
So there's no stating that we had no idea. There was a ton of ideas, okay? A whole bunch of ideas. And you somehow have chosen one particular idea, and the argument is you chose way too quickly. You really didn't look at the evidence fairly, because you were trying to bend it towards this purpose, okay? So, I mean, clearly Young, who did the double slit, was a wave guy, okay? Maxwell, wave guy, all right? I mean, in terms of ethers. So, these were people who believed in this crap, and they shaped the evidence and arguments to justify what they believed it to be, but it isn't fair or the truth. I mean, Young's drawings of water waves comparing to light is completely irrational. It doesn't work. You can't use two waves and explain the double slit pattern. It doesn't work with two waves.
Really was. Figures like Newton and Huygens were...
So gigantic, in a way, controversy between the two. And yes, they were always polite to each other and all that horse crap. But they really didn't see the universe the same way in so many respects. And it's just silly not to acknowledge that.
With light in the 17th century. But a more...
So let's look at the dates. 1695. So Huygens was a bit older than Newton. Yeah, but not that much. It's only 10 years difference, right? Yeah, well, 14 years difference. I think they only met once, I think.
Sophisticated description of light, which we call classical electromagnetism.
So again, they turned it into electromagnetism when induction and all these other functions, magnetism, are different patterns of light, but they're not all of the same. There's no point in saying it's the same thing, okay? I mean, obviously radio is a frequency, but it's not doing exactly the same thing, because only metals can see the radio waves. Only certain configurations of matter can see it. So you have to recognize that some of it is dependent on frankly using metals and things like that to be able to see the pattern, like magnetism. Only a specific, certain kind of substances can see the magnetism. And if you want to make something that's non-magnetic see it, you have to put electricity through it to change its, structure to make it capable of being magnetically influenced, seeing the difference in the pattern.
Was developed largely by James Clerk Maxwell in the 19th century.
So all of that was based on Faraday's work with, creating the first motor and different things like that, finding the different properties of these, the functions. So the idea that the electricity goes this way and the magnetic field goes that way, perpendicular to the flow of the electricity, all those kinds of little subtle facts, but all of those can sort of be understood that, yes, the electricity is going this way, and what's it doing to the atoms? Well, it's making them do this. Okay, as the electricity pushes on them this way, the atoms expand this way, and you can understand that's why they're pushing into the environment and blue shifting the energy coming in.
This theory depicts light as a transverse wave.
So this doesn't even make any sense. This transverse versus, two different fields, all of this mush. And, in what medium? How is it doing any of this? What are you talking about? These fields of nothing? I mean, it doesn't make any sense at all. Water doesn't do this. Nothing, sound doesn't do this. So why is this the diagram?
Composed of oscillating electric and magnetic fields.
So there's nothing oscillating, and clearly, he has to account for radio, he has to start making those little humps 10 miles long. Yeah, there's none of that's happening. It's these are events. The peaks are, you could say, the points on the line, either one. There's an event. There's an object. The object is the frequency between objects. The distance between objects is the frequency. There's no 10-mile long photon. There's just 10 miles between an event and then another event, a compression of force and then another compression of force. That's the signal. That's what's traveling through space. A bunch of elements that have been compressed in the space they occupy by some force that pushed them into compression,
which are at right angles to each other and perpendicular to the direction that the wave moves.
So just nonsense, really.
We'll learn more about these fields later. Just like the kinds of waves we have previously discussed, electromagnetic waves have amplitudes, wavelengths, and frequencies.
So wavelength and frequency is just redundant. So it's just silly talk in a way. All there is the frequency, and that dictates whatever a wavelength is going to be. And the period, these are all redundant. These are all synonyms. They're all words for exactly the same thing. So why have 3 words for the same exact thing? Amplitude's a little different. And so again, that would be in different circumstances. For radio, that would be the number of little bits there are that are moving, would be the amplitude. But something like visible light, okay, there's not going to be any amplitude. There's just going to be the number of these photons, these 3 events hitting a surface in the right sequence, the right polarization. So the amplitude is just going to be dependent on how many times that event hit a surface. But there's not going to be any amplitude in each one of the photons. They don't have any amplitude. They're just discrete one dots. They're just bits of force. So an ultraviolet light photon doesn't have more energy. It just makes the thing happen in a shorter amount of time. So it delivers the energy in a shorter amount of time. And again, if you just think of the tipping point argument, clearly if you're tipping something, if you hit something and it moves and then it starts to slow down, you can understand that it's lost velocity. And so if you hit it again, you're not going to be able to get as much velocity because it's already slowed down. But if you hit it very quickly before it slows down, then you can add quite a lot of energy to it and make it go faster and faster. So obviously gamma rays and X-rays and all these things, they don't have more energy. They're delivering it in a shorter period of time before electrons can move back into their position. So they're moving out with a high velocity. You hit them again before they slow down, then their velocity increases or doubles, and then you can triple their velocity, that kind of thing. So obviously in a tipping point circumstance, you can easily tip things over if you throw 3 rocks real fast at some object. And if you throw it slowly at some object that can oscillate, then it'll stop, and you can oscillate it and then stop and oscillate it, but it won't tip over. So I think that's a very close analogy to the actual function. Just hit the button.
But instead of different frequencies producing different pitches, like sound waves, different frequencies...
So there was a moment there when he showed the little gray bars of consolidation at absence. So, push, consolidated force, going back, less force. That simple argument. So you're creating the null by going backwards, no reflection. I go forward, I quadruple the reflection. I go back, no reflection. And that's basically all you're saying. If I could physically move my hand the speed of light, you could understand that if I moved it this way, my hand would be invisible. Nothing would reflect off of it, right? And then if I moved it this way, everything would be reflecting here where I stopped. Nothing, because my hand's moving the same speed as the light. The reflections could never leave my hand, and they have to wait till my hand stopped before those reflections could reflect. So you could understand it would be all or nothing. All or nothing. And that's what electrons are doing.
Frequencies of electromagnetic waves produce different kinds of light.
So there's no waves doing it, and the frequency is just, you can easily understand that there's no reason why our eye can't create mechanisms, just like the colors on my shirt. It can create chemistry that will collect different colors of light and be, create electricity by them, and other colors that would be ignored, and so that we can have an idea of those subtle differences in those frequencies. And that the key point is the sun creates a lot of this kind of light, red, green, and blue. There's a lot of visible light coming out of the sun. That's why we see visible light. And the other reason why we see it is because any higher frequency, and it starts to ionize our atoms. So it's very destructive to the atomic structure. It starts breaking atoms. So if we saw in ultraviolet, we'd have to have some mechanism to fix all the atoms that were getting wiped out by the ultraviolet light. It would be likely to be causing cellular damage is the problem. Catch us on fire even. So yeah, it's a little bit too much energy too quick. And infrared is too wide a polarization, and so the pixels are too big. So you're not going to be able to see with any kind of detail because the pixels are almost gigantic.
If the light is visible, these frequencies will correspond to different colors. Frequencies greater than this.
So our brain makes color. There's no real color. There's just this idea that some things, the frequencies can constantly be increased by a certain amount, and that's essentially what we see, is the difference between the broad category of this color, this frequency, and the fudge in between.
Will exist as UV radiation, X-rays, or gamma rays, and frequencies less than this qualify as infrared radiation, microwaves, or radio waves.
So the point I would make, or the argument I would make, is that the universe is stuffed full of that infrared radiation and the microwave background and radio. There's a ton of photons hitting surfaces in those lower frequencies, and it's only by something being hot and having a lot of motion in its electrons that it's possible to increase those wavelengths to the visible spectrum and beyond. You need something almost explosive to create X-rays. You need to almost particularize atoms. You need to kind of almost destroy a surface to start creating very high frequency photons, but you need to move electrons very fast to compress to an X-ray or a gamma ray. So they're only going to be created by very, very fast electrons, nearing the speed of light electrons.
All of these phenomena are collectively referred to as electromagnetic.
So you can sort of understand that in like a linear accelerator where they accelerate electrons, that the electrons are making, X-rays and gamma rays and all other kinds of rays, because they're pushing on the force at this incredible speed and increasing all of the radiant thermal energy, the low frequency radiation, into high frequency radiation. And that's why they have to have a couple of feet of brick wall between them and the source.
Magnetic radiation, and they can be found on the electromagnetic spectrum.
So it's just a spectrum of frequency, and it's just such a fraud and a wrong to sit there and demonstrate this as being a wave phenomenon. Nothing is doing this or this or this or any of that crap. It's just a clump and a clump and a clump separated by a distance, and the polarization would be a separation in time, you could argue.
Here we can see all the wavelengths and frequencies ranging from radio waves to gamma rays, and we have found some technological use for all of these in modern society.
So, but the real question is, especially these charts too, don't really show you how tiny the visible spectrum is relative to the bandwidth of all the other spectra. So this doesn't give you a very good detail of how many units of change there are, how many inches of the amount. So, the visible spectrum is a millimeter, the infrared spectrum is, a meter. 1,000 times more frequencies, more units of diversity exist in that range.
Even though they seem dramatically different, some requiring things like antennas or other equipment to manipulate.
Right, so it does make them pretty different, okay, in terms of the fact is you're hitting a surface and the entire surface is collecting the energy versus one tiny place on a surface collecting it. So you're creating electricity in a direction in an antenna, which means it has to go through crystals to be converted into having a direction, that kind of thing, versus hitting a surface, creating what you could argue is electricity, but it has no conductor. It has no plus and minus, so it can't find a direction. But that's sort of the phenomenon. When these little bits hit the surface, the first one pushes on an electron. That pushes an electron in this direction, like electricity. And the next one pushes on the side, expanding it in this direction again, giving the electron more velocity. And the next one, the last one, finally shows up when it's here. It hits, squishes that atom squishes its electron a little faster. So that's essentially why there's a photoelectric effect, in the sense of that's why you have to have a certain frequency of light to be able to eject electrons, is because they have to show up hitting at the right sequence behind the atoms, and it depends on what kind of atoms you're hitting will decide how much energy you can give the electron. So each metal has a little bit of a different range because the atoms are a little different sized, but the idea is they're all conductors. That is, they all tend to move the electricity in one direction or the other. They polarize it. All right, what else needs to be said? So this is just the tipping point argument just going sideways. I mean, I really shouldn't have to. The simple point is when the atoms normally looks like this, let's say, this piece of energy hits the atom and essentially squishes it. So you can understand the electrons have changed their positions. Okay, so this one squished in, it squished this one out. So this one now has a velocity. The next one comes in, it pushes this atom. Now this electron pushes on the other electron of the next atom and pushes it with a velocity. So this one adds a velocity of, say, 20, and then this adds another 20, and then this one adds another 20. So you can see that you get a velocity of 60. Where if just one hits and it goes back to its original position, that's all that happened. So, and it's going out in a circle probably, in different directions to some extent. Well, I probably shouldn't go that far. But the fact is the atom has probably got electrons moving in these other directions, so other photons can land in different places, and it'll create a bit of electricity going in that direction. But like I said, metals make it pretty sure that the fact that the metals are all crystals means that the energy goes in this way and it goes out that way. So it's just the same thing as the piezoelectric effect. You know, twisting a crystal can create electricity. It's because of the crystals that the electricity is capable of being multiplied.
All of them are fundamentally the same thing as the light you can see with your eyeballs. They are just of different wavelengths.
So it really isn't, because the radio, you could argue that it's just all the electrons are hitting. You know, so the whole surface gets hit with electrons and makes a total of pressure on all of the electrons. So it's a little different, I would argue. Polarization becomes less relevant. It's antenna polarization. You have to be aligned with how dense the densest part of the field, and the densest part of the field is radiating out of the antenna. So obviously, if you're in the direction the other antenna's in, you'll get a strong signal. If you're counter to that direction, you get a weak signal.
All electromagnetic radiation moves at the speed of light, which is about 300 million meters per second in a vacuum, the fastest speed possible in the universe. This is fast enough to get from here to the moon in about a second. And since we know that all waves move at a speed...
So all waves, they're not waves. Waves require a medium. You have to explain what the medium is. You're saying the medium's made out of two different fields of what? I mean, it's just a nothing explanation. When you know that charge has to be created by something, there has to be something that tells electrons when they look at another electron that it's looking at an electron. You have to know it has to see. They have to see each other. There has to be some mechanism, and they know they see each other at the speed of light. They don't see each other at some other speed. Now, everything reacts at that speed of light. So clearly that's all the information is carried by stuff moving the speed of light.
That is equal to their wavelength times their frequency.
So it's just ridiculous to, you just have two inverse statements. The wavelengths fraction gets bigger as the frequency fraction gets smaller. It's just nonsense.
This product will be equal to the speed of light for any type of electromagnetic radiation. How is it that electromagnetic radiation is produced?
There, big problem. So this is the part where they just make up some idea that there's this energy of a photon, but there has to be some kind of, you have to explain what this field is that you're putting the energy into. And my simple argument is the field is the energy already in the universe. That's the field. You're just playing with the ping pong balls. So you just think of the universe made out of ping pong balls, and you got baseballs are the matter, and the ping pong balls can stick to the baseballs, blah, 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 blah. And they're going to just push everything around. And when the baseballs move, if they're going to reflect those little bits, because they're moving against, means they have energy in a direction. So if they hit any force coming at them, they're going to reflect it. And, those simple arguments work very well.
To answer this question, we have to learn about electric fields, which are...
Yes, and they'll make a mess out of that. So this is a good drawing just because it shows them a straight line force perpendicular from the surface, and that's exactly what the R² rule indicates, is spherical objects or point particles would look identical, and that's the whole point, is it would be perpendicular. So that's all over the place in Maxwell's equations, is that the force is perpendicular to the surface. So this idea of a field line having some wavy thing goes over here and it loops over there and does all that, that's not a field that actually exists. That's not a motion that actually exists. The only thing that actually exists is this straight line force radiating from electrons and protons. And one of them isn't producing the force and one of them consuming it. They're both producers, and they just have to have an inverse relationship to the same force.
Are coming up soon. For now, let's check comprehension.
So that's a waste of time, really. So we won't bother with that. All right, so let's play the other one since we are here and see what the next video is. All right, so this video is on colors. So he spends whatever it was 3.5 minutes on the whole subject of light, and then spends 5 minutes, 5.5 minutes on color, which is almost superfluous. It's not saying much. We just know that color is just the fact that through evolution, there was advantage in being able to distinguish between the different frequency of radiation coming off of objects, and that would give us information, what something was made out of, and lots of other kinds of information. So it was very useful to have that information. So that's why we can see colors, is because distinguishing the subtle differences in frequency has advantage, because it means it's different chemistry, it's different texture.
Previously discussed the electromagnetic spectrum, and if we zoom in on the visible portion, we see some familiar colors. The order of these colors can be remembered with the mnemonic Roy G. Biv. This stands for red, orange, yellow, green, blue, indigo, and violet, which lists the visible colors from lowest frequency to highest frequency.
So obviously there's lots of other mixtures of colors, and the only colors that are really important are the primary colors, but whatever.
So how does this correlate with the colors of objects? Well, as it happens, most illuminated surfaces will absorb some light and reflect some light.
So the absorption is always just for temporary, right? So you could always argue that you're always at equilibrium. We get hit by lots of light, we don't keep the energy. So all we're doing is re-radiating a visible photon as infrared radiation eventually. So, that's really all that's taking place. It's just, you're just saying some of the light instantly reflects because the electron is rejecting it wholeheartedly. Other light will do something else because the electron is obviously absorption, so that's going in the same direction, and then there's going to be an impact inside the object, right? As it's moving towards the material versus moving away from the material. And so, some of it's going to be reflected later, and probably not at some perfect angle,
depending on the material's properties. When reflection occurs, we can always define an angle of incidence and an angle of reflection, where the angles can be measured with respect to a vertical line perpendicular to the reflecting surface.
And we know it's straight up and down is clearly works really well. All right, so it implies that it has to be at an angle to reflect, and it doesn't. It's just that if you want to increase the amount of reflection, there's a certain angle where all of the light will be reflected because none of it's going to get stuck going in. It doesn't go into the surface enough to be reflected. So it's hitting the electrons sideways more than it's hitting them down. And that's the reason why it doesn't. But you can understand that the surface is essentially elastic, and what you're doing is throwing energy in, pushing on those atoms, pushing on those electrons, and that the surface is going to push back just like the Earth. And when it pushes back, it's going to do exactly the same thing that went in is the same thing coming out. Right now I'm sitting in a chair, the gravity's pushing me in, and the Earth is pushing me back up. So essentially I'm being reflected off of the Earth.
And these angles will always be equal to one another. But as we said, light can also be absorbed, and many materials will absorb only particular colors while reflecting others. The colors that are reflected are the ones we see.
So again, this is you could say on resonance and off resonance. So this has a lot to do with how much they're vibrating. So it's like microwaves being absorbed by water. It has to do with the fact that there's a frequency that the water's oscillating at, likes to oscillate at because of the distance between the electrons. And if you put the energy in at that frequency, you can keep adding more and more. But if it's some sub-frequency or not a harmonic, then it just creates chaos and it doesn't add energy.
When you see a green object, like a leaf, it's because green is the predominant color that is not absorbed, but rather reflected to meet your eyes, and not because there is some inherent greenness to the leaf.
So The argument is that the different chemical compounds will be at resonance in terms of how they're vibrating. Their electrons can vibrate, and you can get a nice reflection of the energy that went in. So the energy goes in, pushes the electron, and the electron next door pushes back out. So it's just a U-turn for the energy.
If an object absorbs all wavelengths of visible light, it will appear black.
So most things that are black not because their color is black, it's because their texture is all convoluted and none of the light goes in, but there's nothing to reflect off of. Because it doesn't hit a flat surface. It hits a bunch of it hits a bunch of surfaces. So it's going into a texture, and the texture absorbs all the light.
If it reflects all visible wavelengths, it will appear the same color as the light that is illuminating it. An interesting phenomenon is...
That's why, like shiny black things, right? They're not as black as what's the right word? Flat. A flat black, it has texture, and it's the texture that's really absorbing all the light.
The way light bends as it travels from one medium to another. This is called refraction. If light goes from one transparent medium to another, like from air to water, the light ray changes direction at the boundary.
So you could probably understand it doesn't matter whether it's transparent or not. This is how it absorbs the energy, is at these angles. So the simple point would be is that the electrons are moving in and out of the surface. And so when the light comes in, it seems probable that energy will be given to them in the direction, okay, of the up and down. So if they're going in and being absorbed, that is, they're going in the same direction as the electron is moving and adding energy to it, then it's going in. Well, that's combining two vectors. So you can understand it's the vector of the energy of the electron plus the vector of the force that gave the electron a little bit more energy. So that's why there's a difference. And instead of speeding the electron up, it slows it down in the sense that the light travels through the medium slower just because it's going to keep going between electrons and force. So the electron moves slowly, some percentage of the speed of light, 25%, 10%, and then the force between the electrons is at the speed of light. So this part is really, so there's a little bit of movement in the electron. The force conveys that at the speed of light to the other electron. The other electron moves, 10% the speed of light. Then the force, and then the electron, then the force. And if you add up all the little slow motions of the electron, that's why it takes longer for the light to get through the medium, is because it has that little part where it's moving actual electrons, and moving the electrons is a lot slower than the speed of light. So the energy doesn't move slower than the speed of light. It's just that it has to, the Sisyphus goes the speed of light when he's not pushing a boulder. When he's got to push an electron, he's going 10% of the speed of light. And that's the difference. That's why the trip takes longer. It's because even though most of the trip is force between electrons, the tiny bit of movement of the electrons is so much slower that it slows the progress of the force. I think that's the rational explanation.
The angle of incidence will be measured as we mentioned before, but instead of an identical angle of reflection, there is a new angle of refraction.
Right, and the angle is basically, you could just see it as a vector. You're just saying I'm increasing the energy, and if I increase the energy, it's going to bend down. That's the energy of the electrons. The absorbing electrons have to be moving the same direction that the energy hitting is in. They have to go in the same direction. So you can understand the electron already has motion in this direction. You hit it with a particle of force and add velocity to it. So you're increasing the speed of the electron, but the electron still has to travel through the dense medium by pushing electrons against electrons. So one electron has to push on the other electron that electron moves, and then the next electron moves. No electron jumps. It's just one electron pushes on another electron. Like magnets. You could put a bunch of north-facing magnets in a little tray, and you can have one magnet push on all the other magnets.
This will happen anytime light's velocity changes, as light moves a little bit more slowly through water than air.
So the electron's moving faster. That's why you have this slighter angle. But the fact is, it's still got to go through a denser medium, so it's going to take longer to get through it.
Which explains why objects in the water sometimes appear to be closer than they actually are.
And yeah, so there's lots of optical effects created by the traveling through the denser medium. And the same effect happens when it leaves. So you can understand when it's going into the lighter mediums, the heavy medium's pushing into the lighter medium, and so it's adding energy going in the direction of the lighter medium. That's the only way the lighter medium could absorb the force.
Light travels even a bit more slowly through glass. This is why a prism is able to split up white light.
So that has nothing to do with the speed that it travels through the prism. It has to do with the exact point of impact and the exact point of leaving. And that's all. The going through part is just, they're all slowed down the same. There's no bending inside the glass. So once it's heading in a direction, it's just going to go a straight line through the glass, and it's just how much glass it has to travel through, period. But there's absolutely no slowing down of the actual force. It's just you're slowing down the part where you have to move electrons. But the angle is already decided at the surface. The surface makes the decision. And the slowness has nothing to do with the bending.
Into all the individual colors it contains, because when light hits the prism at an angle, the different wavelengths of visible light are slowed down by different degrees.
So it really just has to do again with the tipping point argument. The higher the frequency, the faster the electron moves. The lower the frequency, the slower the electrons are going to move. And that's all you're really doing, is changing the speed at which how much energy you're adding in one direction versus the other directions.
And thus have slightly different angles of refraction. This causes the colors to fan out such that they are individually visible.
So the blue light bends more and the red light bends less. Okay. So that is, part of how you have to explain the event. And so the reason why the blue light bends more is because the event on the surface has more of that direction.
Since white light can be refracted to separate...
That wasn't quite right, so yeah, just ignore that sentence.
...all the colors, it should follow that all the colors can be combined to get white light. This is true of the additive primary colors, which are red, green, and blue. If we pass light through a red filter and combine it with light through a green filter, we get yellow light. If we combine this with light...
So these are the absorption filters. So again, it makes it a little bit complicated because you really have to use the complementary colors if you're going to paint to get white. If you add all these colors, you end up with black, not white. But anyway.
Passed through a blue filter, we get white light, which makes yellow the complementary color of blue. In this way, each pair of primary additive colors combines to give the complement of the third. It is the combination of these colors that allows us to see all the others, because our eyes have three kinds of color receptors, each of which is sensitive to red, green, or blue light, which can be stimulated in various combinations. When we create...
And they're hunks of this spectrum, so you're talking about 200 nanometer hunks of difference in their frequency, so it's a pretty good range of difference.
art with various materials, these combinations will be different because paint and wax and other material substances exhibit a certain color because of the light they reflect, unlike the actual beams of light we discussed. So when mixing paints, blue and yellow
absorbing is different than reflecting.
Will give green rather than white. All three of the subtractive primary colors, cyan, magenta, and yellow, when combined, will subtract all of the colors from white light, and the mixture will appear black. So the next time you do some painting or see a rainbow, give a moment's thought to the electromagnetic waves that produce all of the vibrant colors we have grown to appreciate.
Blah, 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 blah. So, I mean, what that is, I don't know why that's in a physics video, but whatever. We should appreciate.
Let's check comprehension.
No, let's not. All right. So, anyway, let me give a pause, and I'll see if there's anything I need to throw in here as a point to be made. But the argument is that the universe is made out of real things, just things, and the things are, the things are, and when they're force bits, okay, when the thing is a bit of force, okay, it's moving the speed of light, unless it's stuck to a piece of matter, and then it's moving some variable speed depending on how much force has been collected, how many Sisyphuses are pushing the same boulder. The boulder goes faster, the more Sisyphus pushing it in a direction. And there can never be a Sisyphus on either side of a boulder. There can only be Sisyphuses on one side or the other. So an electron can only move in one direction in one dimension. Whoa, and that's it. All right, pause. All right, so I think I'll go over the refraction part with a little more detail, just because I left that a little confused in terms of understanding. Okay, so the light comes in this way, and blue goes this way, let's say, and red goes more like this. Okay, so the blue is bent more than the red is bent, and the argument would be, okay, is that's happening because of this angle that the light's coming in at. So the light's coming in this way. It's hitting an atom. Again, just a simple explanation. But the atom gets hit this way, which means the electrons will go this way and this way. So that's the angle. So you're adding more energy because you're hitting twice very quickly. So you're adding more force this way. That's why the blue goes this way, is because you hit twice quickly, or 3 times, whatever a photon is. And that means that you've caused the energy to have a higher velocity, the electron to have a higher velocity in this direction. So the component this way is higher in the blue light, and the component this way in the red light is lower because of the less energy going this direction from this angle. So again, it's always this perpendicular thing. So it's not going to move perfectly perpendicular, because the electron has motion this way first, and now you're adding, okay, motion this way. So you're adding 2 vectors. And so you have to recognize that you're going to end up with a composite of those 2 vectors. And that's why the blue light bends more and the red light bends less, is because the blue light is coming in. So whatever the angle is, the blue light's going to have a sharper trajectory off of that angle, because it's the perpendicular component to the angle that you're adding to the electron. If you pay attention to that, it is accurate. Okay, but yeah. How much attention you're willing to pay, who knows. So anyway, enough of a video and such. So till the next time, we're almost another 5 or 6 videos and we're done with this asshole. He is an asshole. I mean, frankly, these are all legitimate subjects. They've closed the door to discussion of these subjects because they believe in a woo-verse, and they're religious fanatics, and they won't have their understanding altered by facts. And that's the truth of it.